Right now, somewhere in the observable universe, a star is dying. Not slowly, not gracefully. Its core is collapsing at 70,000 kilometers per second, and within a fraction of a second, it will release more energy than our sun will produce in its entire 10 billion year lifetime. The explosion will briefly outshine every other star in its galaxy combined. It will forge atoms that do not exist anywhere else in the universe at that moment. And when the light fades, what remains will be something so extreme that the laws of physics themselves bend around it. This is not a metaphor. This is not a dramatization. This is confirmed by astrophysics. And what really happens inside that dying star is far stranger than any explosion you have ever imagined. If you enjoy journeys into the most violent and beautiful physics the universe has to offer, consider tapping the like and subscribe button. It genuinely helps this channel keep bringing you stories about the cosmos. Now, get yourself nice and comfortable. Let's begin. Look up tonight. Find a star, any star. Watch it for a moment. It looks calm. It looks still. It looks like it has been sitting in that exact position since the beginning of time and will remain there long after you are gone. Every civilization in human history has drawn the same conclusion. The Egyptians used stars to align their pyramids because they trusted the sky would not change. Polynesian navigators crossed thousands of miles of open ocean because the stars were reliable markers that never moved. We named our constellations after gods and heroes because we assumed the patterns were eternal. Every lullaby ever sung under a starlit sky carried a hidden assumption. The stars are safe. The stars are permanent. The stars will always be there. This assumption is wrong. Not slightly wrong. Fundamentally, dangerously, spectacularly wrong. Every star you see tonight is a temporary object. Every one of them was born, and every one of them will die. Some will fade gently into cosmic retirement. Others will die in ways so violent that the human mind lacks any adequate reference point for the destruction involved. And the difference between a quiet death and a catastrophic one comes down to a single factor that was determined before the star ever produced its first photon of light. Mass. That is the dividing line. That is the verdict written at birth. A star's mass determines how it will live, how long it will burn, and how it will die. And for the most massive stars in the universe, the ones that blaze brightest and burn hardest, the sentence is already decided. They will explode. Not gently, not gradually. They will undergo one of the most violent physical events that the laws of nature permit. But to understand why that explosion happens, and why it is not just a dramatic flash but the catastrophic failure of an object that held itself together for millions of years, you first need to understand what a star actually is. Because a star is not what you think it is. You think a star is a glowing ball of fire. It is not. Fire is a chemical reaction. What happens inside a star is something entirely different. A star is a nuclear furnace. Deep in its core, under pressures and temperatures that have no equivalent on Earth, atomic nuclei are being forced together with such violence that they merge into heavier elements. This process is called nuclear fusion, and it is the engine that powers every star in the observable universe. Our own sun converts roughly 600 million tons of hydrogen into helium every single second. During that conversion, a small fraction of the hydrogen's mass is transformed directly into energy, following the most famous equation in physics. That energy radiates outward as light, heat, and radiation. It is the reason Earth is warm. It is the reason plants grow. It is the reason you can see anything at all. But fusion does something else. Something that matters far more for the story we are telling. Fusion produces an outward pressure. The energy generated in the core pushes against the star's own material, pressing outward in every direction. This outward push is what prevents the star from collapsing under its own gravity. And this is the critical detail that most people never think about. A star is not a stable object, peacefully glowing in space. A star is a var. Every second of every day for millions or billions of years, two forces are locked in a fight to the death. Gravity pulls inward, trying to crush the star into the smallest possible volume. Radiation pressure pushes outward, trying to blow the star apart. The star exists only because these two forces are perfectly balanced. Physicists call this state hydrostatic equilibrium. It sounds clinical, it sounds stable, it sounds safe. It is none of those things. It is a ceasefire between two forces that will never stop trying to win, and one of them always does. For a star like our Sun, this balance holds for a very long time. The Sun has been burning hydrogen for roughly 4.5 billion years and will continue doing so for another 5 billion. It is a middle-aged star living a comfortable, unremarkable life. When it finally exhausts its hydrogen fuel billions of years from now, it will swell into a red giant, shed its outer layers into space, and leave behind a dense, cooling remnant called a white dwarf. No explosion, no catastrophe, just a slow, dignified fade into darkness over trillions of years. Most stars in the galaxy will die this way. Roughly 97% of all stars lack the mass to do anything more dramatic. They burn their fuel, puff off their outer layers and quietly retire. But the remaining few percent are different. These are the massive stars. Stars born with more than approximately 8 times the mass of our Sun. And they do not die quietly. They cannot. Their mass guarantees a different fate. A fate written into the physics of how nuclear fusion works at extreme scales. These stars burn brighter, burn hotter, and burn through their fuel with a recklessness that seals their destruction. To understand why, you need to grasp a counterintuitive truth about stellar physics. The more massive a star is, the shorter its life. This seems backward. A bigger star has more fuel, so it should last longer. But massive stars do not just have more fuel, they burn it exponentially faster. The core temperature and pressure inside a massive star are so extreme that fusion reactions proceed at rates that dwarf anything happening inside our Sun. A star 10 times the mass of the Sun does not burn 10 times faster. It burns roughly 3,000 times faster. A star 25 times the Sun's mass exhausts its fuel not in billions of years, but in roughly 7 million years. That sounds like a long time by human standards, but in cosmic terms, it is practically nothing. The Sun has already lived 600 times longer than some of these giants will ever exist. And here is where the story turns dark, because massive stars do not just burn hydrogen. When the hydrogen in their core runs out, they do not simply stop and begin their retirement. Instead, gravity squeezes the core harder, the temperature rises, and a new fuel ignites. Helium. The helium that was produced as a waste product of hydrogen fusion becomes the next fuel source. The core begins fusing helium into carbon and oxygen. The star stabilizes again. Equilibrium is restored. The war between gravity and pressure reaches another temporary truce. But this truce is shorter than the last. Helium fusion in the core of a massive star lasts roughly 1 million years. Compare that to the millions of years of hydrogen burning that preceded it. The clock is already speeding up. And when the helium is spent, the same pattern repeats. Gravity squeezes. Temperature rises. The next fuel ignites. Carbon fuses into neon, sodium, and magnesium. This stage lasts roughly 1,000 years. Then neon burning begins, lasting perhaps a single year. Then oxygen burning, which sustains the core for a few months. Each stage produces heavier elements. Each stage releases less energy per reaction than the last. Each stage lasts a fraction of the time of the one before it. To feel the true horror of this acceleration, you need to see the conditions inside the star at each stage. When the core burned hydrogen, temperatures hovered around 35 million degrees, hot enough to sustain proton-proton chain reactions that gradually converted hydrogen nuclei into helium. The core was dense but stable, humming along with an efficiency that could sustain itself for geological ages. When helium ignition began, the core temperature had climbed to roughly 200 million degrees. Helium nuclei carried twice the electrical charge of hydrogen nuclei. which means they repel each other more strongly. The core must reach far higher temperatures to force helium nuclei close enough for the strong nuclear force to bind them. The famous triple alpha process fuses 3 helium nuclei into a single carbon-12 nucleus through a 2-step reaction, so statistically unlikely that it requires a specific resonance state in the carbon nucleus to proceed at any meaningful rate. Fred Hoyle predicted the existence of this resonance in 1953, before it was experimentally confirmed, arguing that it had to exist because carbon clearly exists in the universe. He was right. Without that resonance, stellar nucleosynthesis would stall at helium, and the universe would contain no carbon, no oxygen, and no life. The physics that allows stars to build elements heavier than helium depends on a nuclear energy level that Hoyle deduced must be there simply because we are here to ask the question. When carbon ignition begins, core temperatures exceed 600 million degrees. At these temperatures, carbon nuclei fuse to produce neon, sodium, and magnesium in a complex web of competing reactions. The energy yield per reaction is smaller than helium burning, and the neutrino losses from the core are increasing sharply. At these extreme temperatures, the core produces neutrinos through processes that did not operate significantly during earlier burning phases. These neutrinos escape the star immediately, carrying energy directly out of the core and into space, without contributing to the outward pressure that holds the star up. The star is now leaking energy through a channel it cannot plug. Each successive burning stage increases the neutrino losses further, making the fuel burn faster to compensate, which produces more neutrinos, which forces even faster burning. The star is caught in a feedback loop that it cannot escape. Neon burning follows at roughly 1.5 billion degrees. The process is peculiar. Neon nuclei are not fused directly with each other. Instead, the intense thermal photon field inside the core begins disintegrating neon nuclei through photodisintegration, breaking them into oxygen and helium. The released helium nuclei are then captured by surviving neon nuclei to produce magnesium. The core is simultaneously destroying and building elements, tearing apart the products of one burning stage to fuel the next. The star is cannibalizing its own interior chemistry. Oxygen burning drives temperatures beyond 2 billion degrees. Oxygen nuclei fuse to produce silicon, sulfur, phosphorus, and other intermediate mass elements. The reactions release gamma-ray photons so energetic they contribute to a radiation field that is itself becoming a significant component of the core's energy budget. The neutrino losses from the core during oxygen burning are so severe that the star radiates more energy in invisible neutrinos than it produces through fusion itself. The core is now spending faster than it earns, burning through its remaining oxygen in a matter of months while hemorrhaging energy through a channel that provides no structural support whatsoever. The core is now fighting not only gravity but its own radiation field turning against it. And then silicon burning begins at 3 billion degrees and lasts a single day. But the statement that silicon burning lasts one day conceals something even more disturbing. The very final phase of silicon burning, the frantic accumulation of the last fraction of iron in the core, takes not a day but hours. In the final hours of the star's life, the core temperature exceeds 5 billion degrees. The nuclear reactions are so fast and so numerous that the core's composition changes on timescales measured in minutes. An object that maintained structural stability for 7 million years is now transforming its own chemistry faster than a human heart beats. The star does not know it is dying. It has no awareness, no sensation, no capacity to register what is happening. But if it did, it would feel the floor dropping away beneath it with each passing minute. The fuel is running out, the furnace is failing, and gravity, which has waited patiently for millions of years, is about to collect. Think about what is happening here. A star that burned hydrogen for 7 million years is now cycling through successive fuels in millennia, then years, then months. The pattern is not linear. It is exponential collapse, an acceleration toward a wall that the star cannot see but cannot avoid. Every new fuel is less efficient than the last. Every new stage demands higher temperatures and pressures. The star is working harder and harder to produce less and less energy, while gravity waits patiently for the moment when the furnace finally fails. During these late stages, the star's interior becomes an extraordinary structure. The core is no longer a simple ball of fusing material. It has become layered, like an onion. Each shell burns a different fuel. The outermost shell still fuses hydrogen. Beneath it, a helium-burning shell. Below that, carbon, then neon, then oxygen, then silicon. Each layer is hotter and denser than the one above it, and each one is producing progressively heavier elements. The star has become a factory of atomic creation, building the periodic table from the inside out. If you could slice the star in half during its final hours and examine the cross-section, you would see a structure of astonishing complexity. At the very center sits the growing iron core, a ball roughly the size of Earth glowing white-hot at 5 billion degrees, inert and useless, accumulating mass like sand filling an hourglass. Immediately surrounding the iron core is a thin shell where silicon is actively fusing, feeding fresh iron onto the core below. This shell is narrow and ferociously hot, a furnace within a furnace, operating at temperatures that would vaporize any material known to human engineering. Beyond the silicon-burning shell lies the oxygen-burning shell, broader and slightly cooler but still operating at 2 billion degrees. Above that sits the neon shell, then the carbon shell, then the helium-burning shell, and finally, at the very outermost layer, a vast envelope of hydrogen that has been largely untouched for millions of years, still fusing at a gentle pace, completely unaware of the catastrophe unfolding thousands of kilometers below. The distance from the iron core to the hydrogen envelope spans millions of kilometers. The temperature gradient from center to surface covers a range from 5 billion degrees to a few thousand. The density drops from billions of grams per cubic centimeter in the core to wisps of gas thinner than a laboratory vacuum at the surface. Each shell operates independently, burning its own fuel, producing its own waste products, and feeding material to the shell below. The structure is not static. Convective plumes of heated material rise and fall within each shell, mixing fresh fuel downward and carrying reaction products upward. The boundaries between shells are not sharp lines, but turbulent transition zones where different nuclear reactions compete for dominance. The entire configuration is dynamic, pulsating, adjusting to the shifting balance of pressures and temperatures that change with each passing hour. It is a machine of extraordinary intricacy, built by nothing more than gravity and nuclear physics. A machine that has been running for millions of years and has less than a day left to operate. Elements that took the universe billions of years to accumulate are being manufactured in real time inside this dying furnace. Carbon, oxygen, neon, magnesium, silicon, sulfur. These elements will matter enormously later in this story. But right now, the star does not care about its chemical legacy. It is fighting for its life. And then comes the final fuel, silicon. When the core reaches temperatures exceeding 3 billion degrees, silicon nuclei begin fusing. The reactions are fast, violent, and extraordinarily complex. Silicon does not simply combine into a single heavier element. The process involves a chaotic series of nuclear reactions called silicon burning, where nuclei are broken apart and reassembled in a frenzy of photodisintegration and particle capture. The end product of this chaos is iron, and here, at the creation of iron, the story reaches its turning point. Because iron is different from every element the star has ever produced. Every fuel the star has burned, from hydrogen to silicon, released energy when its nuclei fused together. That energy is what powered the outward pressure that kept gravity at bay. But iron sits at the very bottom of the nuclear binding energy curve. It is the most tightly bound nucleus in nature. Fusing iron into anything heavier does not release energy. It consumes energy. For the first time in the star's entire existence, the fusion process that has sustained it for millions of years cannot produce what the star needs to survive. The furnace has built something it cannot burn. Silicon burning lasts approximately 1 day. One single day. After millions of years of hydrogen burning, after hundreds of thousands of years of helium burning, after centuries and decades and months of progressively desperate fuel stages, the final act takes 24 hours. In that single day, The core accumulates iron at a furious rate. Silicon shell burning continues feeding iron into the core from outside. The iron core grows heavier and heavier, approaching a mass threshold beyond which nothing in quantum mechanics can prevent gravitational collapse, compressed into a volume no larger than Earth. And then it crosses that line. But before we reach that moment, look up again. Find Betelgeuse. If you are in the northern hemisphere, it is the bright reddish star marking the shoulder of Orion. You have probably seen it 1,000 times without thinking about it. Betelgeuse is a red supergiant, a massive star in the late stages of its life. It has already exhausted the hydrogen in its core. It has swollen to a diameter roughly 1,000 times that of our Sun. If you placed Betelgeuse where our Sun sits, its surface would extend past the orbit of Jupiter. It is enormous, luminous, and unstable. For years, astronomers wondered whether Betelgeuse was on the verge of exploding. In late 2019, the star dimmed dramatically, dropping to roughly 40% of its usual brightness. Headlines erupted. Social media buzzed with supernova speculation. Was this the end? Was Betelgeuse about to become the most spectacular astronomical event in 4 centuries? The answer turned out to be no. Scientists later determined that the dimming was caused by a massive cloud of dust ejected from the star's surface, temporarily blocking its light from our perspective. Betelgeuse was not dying. It was sneezing. But the story took another turn in July 2025, when astronomers using the Gemini North Telescope confirmed something that had been suspected for nearly a century. Betelgeuse is not alone. A smaller companion star, now officially named Siwaha, orbits the red supergiant. Siwaha appears to be a relatively modest star, roughly 1.4 to 1.6 solar masses, likely a hot main sequence star that has been hidden in the overwhelming glare of its enormous partner. The companion's orbital period is approximately 2,170 days, and its presence may explain much of the periodic dimming and brightening that had fueled supernova fears. This discovery matters because it changed the timeline. Some earlier studies had suggested Betelgeuse might be burning its final nuclear fuels and could explode within decades. The companion star complicates that picture. Its gravitational influence affects the material surrounding Betelgeuse, modulating the dust and gas that shape what we observe. The periodic variations in brightness that some researchers interpreted as signs of imminent core instability may instead be signatures of Siwaha ploughing through Betelgeuse's extended atmosphere. The current scientific consensus places Betelgeuse's supernova somewhere within the next 100,000 years. It could happen tomorrow. It could happen long after human civilization has transformed beyond recognition. What is certain is that it will happen. Betelgeuse is too massive to die any other way. When Betelgeuse finally does explode, the event will be visible from Earth with the naked eye. Estimates suggest it could become nearly as bright as the full moon. Visible even during daylight hours, a pinpoint of extraordinary brilliance in the constellation Orion that would persist for weeks or months before fading. At a distance of roughly 550 to 700 light-years, the explosion poses no danger to Earth. We are far too distant for the radiation to cause harm, but the spectacle would be unlike anything any living human has ever witnessed. The last supernova visible to the naked eye occurred in 1987 in a neighbouring galaxy, and before that, none had been seen since 1604. A Betelgeuse supernova would be far closer than either event and would dwarf both in apparent brightness. Astronomers today have neutrino detectors, gravitational wave observatories, and space telescopes that could provide hours or even days of advance warning before the light from the explosion reached us. But Betelgeuse is just one example. The Milky Way contains an estimated tens of millions of massive stars that will eventually meet the same fate. Some are already burning silicon. Some are accumulating iron in their cores right now, at this moment, as you hear these words. Most of them are too far away and too obscured by interstellar dust for us to see. But they are out there, and the physics governing their deaths is identical to what governs Betelgeuse. That physics is relentless. Once a massive star begins fusing silicon, it has less than a day to live. The iron accumulates. The core grows heavier. The electron degeneracy pressure that has been supporting the core against gravitational collapse reaches its physical limit. And what happens next occurs so fast that the word sudden does not begin to capture it. The core does not gradually lose its battle against gravity. It does not slowly compress over hours or days. The failure is instantaneous and total. In roughly 1 second, the inner core collapses from a volume the size of Earth to a sphere roughly 40 kilometers across. 1 second. A structure that has maintained its integrity for millions of years compresses to a density so extreme that a teaspoon of its material would weigh more than 1 billion tons. This is not an exaggeration. This is not poetic license. This is measured, confirmed physics based on decades of observation, simulation, and theoretical work. The collapse happens so quickly that the outer layers of the star do not even know it has occurred. Information travels through the star at the speed of sound, which in stellar material is fast but not instantaneous. The outer shells are still burning their fuels, still fusing elements, still maintaining the layered structure that took millions of years to build. They have no idea that the floor has just dropped out from underneath them. The core has vanished. The center of the star is gone, and gravity is about to collect on every debt the star has ever owed. What follows is the most violent event in the known universe short of the Big Bang itself. But to understand it, to truly feel the physics of what happens in the next fraction of a second, we need to go inside the collapsing core. We need to follow the iron nuclei as they are ripped apart. We need to track the neutrinos as they carry away more energy than the human mind can conceptualize. We need to watch the shockwave form, stall, and face the single most important question in all of stellar physics. Will it restart? Or will the star swallow itself whole? That question is where everything changes. The core of a massive star in its final hours is one of the most extreme environments in the universe. Temperatures exceed 3 billion degrees. Densities reach billions of grams per cubic centimeter. Pressures crush matter into states that do not exist anywhere else in nature, except inside neutron stars in the first moments after the Big Bang. And at the center of all this extremity sits a ball of iron roughly the size of our planet, containing more mass than our entire sun, supported against gravitational collapse by nothing more than a quantum mechanical principle that is about to reach its breaking point. To understand why this moment is so catastrophic, you need to understand what has been holding the core up until now. Throughout the star's life, the outward pressure came from nuclear fusion. Energy released by fusing lighter elements into heavier ones pushed back against gravity. But once the core became iron, fusion stopped providing energy. So what prevented immediate collapse? The answer is electron degeneracy pressure, a force that arises not from energy production, but from a fundamental law of quantum mechanics called the Pauli exclusion principle. The Pauli exclusion principle states that no two electrons can occupy the same quantum state at the same time. When matter is compressed to extreme densities, electrons are forced into higher and higher energy states because the lower states are already full. This creates an outward pressure that resists further compression. It has nothing to do with temperature or fusion. It is purely a consequence of quantum physics. And for a while, it works. The iron core sits in a state of uneasy stability, supported by the reluctance of electrons to be squeezed into the same quantum configuration. But this support has a ceiling. In 1930, a young Indian physicist named Subramanian Chandrasekhar, working aboard a steamship travelling from India to England, calculated the maximum mass that electron degeneracy pressure can support against gravitational collapse. That limit is approximately 1.4 solar masses. Below this threshold, electron degeneracy pressure wins. Above it, gravity wins. There is no middle ground. There is no negotiation. The physics is absolute. The iron core does not sit still at the Chandrasekhar limit. It grows. Silicon shell burning continues at the boundary of the core, producing more iron and dropping it onto the core like snow accumulating on a rooftop. The core absorbs this additional mass and compresses further. Temperatures climb, densities increase. The electrons inside the core are squeezed harder and harder into higher energy states. The degeneracy pressure rises to compensate. but it is approaching its theoretical maximum. The core is a structure under siege, gaining weight it cannot support, heating beyond temperatures it was never designed to withstand. And then two things happen almost simultaneously that trigger the final collapse. The first is photodisintegration. At temperatures exceeding 5 billion degrees, the thermal photons inside the core become so energetic that they begin ripping iron nuclei apart. Iron, the most tightly bound element, the end product of millions of years of stellar fusion, is torn to pieces by the radiation field. The photons shatter iron nuclei into helium nuclei and free neutrons. This process is endothermic. It absorbs energy rather than releasing it. The core suddenly loses a massive amount of thermal energy that was contributing to the pressure holding the core up. In a fraction of a second, the structural integrity of the core takes a devastating hit. The second process is electron capture. As densities climb, protons in the iron core begin absorbing electrons, converting into neutrons and releasing neutrinos. Each capture removes an electron from the population, providing degeneracy pressure. Every electron that merges with a proton is one fewer electron pushing back against gravity. The degeneracy pressure drops. Simultaneously, the neutrinos produced by electron capture initially stream out of the core at nearly the speed of light, carrying energy with them. The core is hemorrhaging both thermal energy through photodisintegration and degeneracy pressure through electron capture. Both pillars of support are being knocked out at the same time. The collapse begins, and it is fast, unimaginably fast. The inner core, roughly the innermost portion containing about half a solar mass of material, begins contracting in what physicists call homologous collapse. Every layer falls inward with a velocity proportional to its distance from the center. The inner core shrinks uniformly, maintaining its density profile as it contracts, but the outer core falls differently. It plunges inwards supersonically, faster than the speed of sound in the material, creating a chaotic, turbulent infall that no signal from inside the collapsing core can outrun. The entire inner core collapses from a body roughly the diameter of Earth to a sphere approximately 40 kilometers across in less than a second. The infall velocity reaches roughly 70,000 kilometers per second. That is nearly a quarter of the speed of light. Material that a moment ago occupied a volume comparable to our planet is now compressed into something barely wider than a mid-sized city. The density inside this collapsing sphere reaches values that exceed the density of an atomic nucleus. At these densities, individual protons and neutrons are essentially touching. The matter has become nuclear matter, a state of existence so extreme that the entire mass of Mount Everest could be squeezed into a space smaller than a sugar cube. And then the collapse stops. The reason it stops is the strong nuclear force. At densities above approximately 270 million tons per cubic centimeter, the strong force between nucleons becomes repulsive at short ranges. Neutrons and protons resist being squeezed any closer together. This resistance is far stiffer than electron degeneracy pressure. It is effectively incompressible. The inner core hits this nuclear wall and suddenly decelerates from a quarter of the speed of light to nearly zero in less than a millisecond. The result is a bounce. The inner core overshoots its equilibrium density slightly, compresses beyond nuclear density, and then springs back outward like a rubber ball striking a concrete floor. This rebound launches a pressure wave into the still infalling outer core. That pressure wave steepens into a shock wave as it encounters material falling inward at tens of thousands of kilometers per second. The shock meets the infalling matter head-on, and for a brief moment, it looks like the explosion has begun. But it has not, and this is where the physics becomes cruel. The shock wave is born with enormous energy, roughly 3 times 10 to the 51 ergs, a number so large it has no meaningful human analogy. But the shock faces a gauntlet. As it pushes outward through the still collapsing outer core, it must do 2 things that drain its energy catastrophically. First, it must plow through the infalling iron and silicon, material that is still plunging inward at tremendous speed. Every gram of infalling matter that the shock encounters must be decelerated, stopped, and reversed. This costs energy. Second, The shock must dissociate the heavy nuclei in its path. As the shock passes through iron and silicon nuclei, the extreme temperatures behind the shock front break those nuclei apart into free protons, neutrons, and alpha particles. This dissociation is endothermic. It drains roughly 1.5 times 10 to the 51 ergs per tenth of a solar mass of material that the shock crosses. The shock is losing energy faster than it can maintain its outward push. Within milliseconds, the shock stalls. It does not die instantly. It lingers at a radius of roughly 100 to 200 kilometers from the center, hovering as a standing accretion shock. Material continues falling through the shock from above, getting heated and compressed as it passes through, then settling onto the surface of the newly formed protoneutron star below. The shock has become a boundary layer, a membrane between the collapsing star above and the ultra-dense remnant below. But it is no longer moving outward. The explosion has failed. At least, it has failed so far. This is the central unsolved problem in supernova physics. For decades, astrophysicists have known that the initial bounce shock cannot explode the star on its own. The shock stalls every time. In every simulation, in every theoretical calculation, the direct mechanism fails. If nothing revives that shock, the entire star collapses inward. The protoneutron star grows beyond the maximum mass that neutron degeneracy pressure can support, and the whole structure disappears behind an event horizon. A black hole forms. No explosion, no supernova, no spectacle. The star simply vanishes. Yet we know supernovae happen. We observe them. We see their remnants scattered across the galaxy. We detect the neutrinos they produce. Something restarts the shock. Something provides the extra energy needed to push it through the infalling material and blow the star apart. The question is what? The leading mechanism is called the neutrino-driven convection model, and it has been the focus of some of the most computationally expensive simulations in the history of science. Here is how it works. When the core bounces and the protoneutron star forms, the newly created remnant is extraordinarily hot and dense. It contains roughly 1.5 solar masses of material compressed into a sphere about 40 kilometers across. This material is so hot and dense that it produces neutrinos at a staggering rate. Neutrinos are ghostly subatomic particles that interact with matter only through the weak nuclear force. Under normal conditions, they pass through virtually everything. A neutrino produced in the sun's core can travel through the entire Earth without hitting a single atom. But conditions behind the stalled shock are not normal. The densities are so extreme that even neutrinos, the most elusive particles in physics, begin interacting with the matter surrounding the protoneutron star. A small fraction of the neutrino flux streaming outward from the hot remnant is absorbed by the material just behind the stalled shock. This energy deposition heats the matter in a region that physicists call the gain region, the zone where neutrino energy absorption exceeds neutrino energy loss. This heating drives convection. Hot, neutrino-heated material rises outward in buoyant plumes. Cooler material sinks inward toward the protoneutron star. The turbulent mixing enhances the efficiency of neutrino energy absorption by continually cycling fresh material through the gain region. The convective motions create pressure behind the stalled shock, gradually pushing it outward. Over a timescale of hundreds of milliseconds, sometimes more than a full second after the initial bounce, the shock begins moving again, slowly at first, then accelerating as it reaches lower density material that offers less resistance. The shock revives. The explosion begins. This process is excruciatingly sensitive to the details. The neutrino luminosity must be high enough to deposit sufficient energy. The mass accretion rate onto the protoneutron star must drop low enough that the ram pressure from infalling material does not overwhelm the shock. The convective patterns must develop the right turbulent structures at the right time. The physics involves general relativity, nuclear physics, neutrino transport, magnetohydrodynamics, and turbulent convection operating simultaneously in 3 dimensions. No pencil and paper calculation can capture this complexity. Only full three-dimensional simulations run on the most powerful supercomputers in the world can approach a realistic model, and those simulations have been producing increasingly revealing results. Early one-dimensional simulations in the 1960s and 70s could not produce explosions at all. Two-dimensional simulations in the 1990s showed that convection could help revive the shock, but the results were sensitive to artificial symmetry assumptions. Only in the past decade have fully three-dimensional simulations become computationally feasible, and they have revealed something that changes everything about how we understand supernova explosions. The explosions are not symmetric. They are not uniform outward blasts radiating equally in every direction. They are chaotic, lopsided, turbulent eruptions. The shock does not revive everywhere simultaneously. It breaks out in one direction first, driven by a dominant convective plume that pushes through the infalling material, while other regions remain stalled. The proto-neutron star receives a gravitational kick from this asymmetry, recoiling in the opposite direction of the strongest explosion. This kick explains a long-standing, observational puzzle. Neutron stars in the galaxy move at remarkably high velocities, often hundreds of kilometers per second, sometimes exceeding 1,000. These natal kicks are a direct consequence of the asymmetric nature of the explosion. An April 2026 study published in Physical Review D demonstrated this sensitivity in striking detail. Researchers simulated the gravitational wave signals produced by core collapse supernovae originating from two nearly identical progenitor stars. Despite having almost the same initial mass, the two stars had developed significantly different internal structures during their final evolutionary stages. One had a more compact core, the other slightly more extended. These small structural differences produced measurably different collapse dynamics, different accretion rates onto the proto-neutron star, different convective patterns, and ultimately different gravitational wave signatures. The more compact core generated larger amplitude gravitational waves and released more gravitational wave energy. The study confirmed that the final outcome of a supernova depends not just on the mass of the progenitor star, but on the specific details of its internal structure at the moment of collapse. Two stars born with the same mass can die in detectably different ways. This is not just a theoretical exercise. Gravitational wave detectors like LIGO and Virgo are actively searching for signals from core collapse supernovae. A galactic supernova would produce a gravitational wave signal detectable by current instruments, and the characteristics of that signal would encode information about the collapse dynamics, the rotation rate, and the convective patterns inside the dying star. Combined with neutrino detections from facilities like Super Kamiokande, IceCube, and the Deep Underground Neutrino Experiment, astronomers would receive a multi-messenger portrait of the collapse in real time. We would not merely see the light from the explosion, we would feel the ripple in space-time and detect the phantom particles streaming from the proto-neutron star hours before the optical brightening became visible. But there is another outcome, one that does not involve an explosion at all. In February 2026, a research team led by Kishalede published results in the journal Science, documenting the most complete observational record ever made of a star collapsing directly into a black hole without producing a supernova. The star, designated M31 2014 DS1, was a red supergiant in the Andromeda galaxy with approximately 13 times the mass of our Sun. Archival observations spanning over a decade showed a remarkable sequence. Beginning in 2014, the star increased its mid-infrared brightness by roughly 50% over a 2-year period. Then it began fading. By 2022, it had dimmed below its original brightness and continued fading. The dramatic and sustained disappearance was consistent with a failed supernova, a scenario in which the core of the star collapsed, but the resulting shockwave was not strong enough to unbind the outer layers. Instead of exploding, the star's core collapsed into a black hole. The outer layers were slowly expelled or accreted rather than violently ejected. Observations from the James Webb Space Telescope in 2026 detected a faint, persistent infrared source at the same location, consistent with dust enshrouding the remnant. The team connected this observation with a similar case. NG C6946, BH1, a star in the galaxy NGC 6946 that had been flagged as a failed supernova candidate 10 years earlier. Together, these two objects suggest that failed supernovae are not just theoretical curiosities but a real class of events that occurs in nature. The implications are profound. Not every massive star that reaches the end of its life produces a supernova. Some of them simply disappear. The core collapses, the shock fails to revive, and the entire star is swallowed. For a distant observer, the star is there 1 decade and gone the next. No brilliant flash, no expanding remnant, no heavy elements scattered into space. Just a quiet vanishing act and a new black hole where a star used to be. Whether a star explodes or fails depends on the details that the April 2026 gravitational wave study illuminated. The compactness of the core, the rate of mass accretion through the shock, the neutrino luminosity from the proto-neutron star, the development of convective instabilities. Progenitor stars in the range of roughly 8 to 25 solar masses generally produce successful explosions, leaving behind neutron stars. Stars above roughly 25 solar masses face increasing odds of failure, with the most massive stars likely collapsing directly to black holes. But the boundary is not clean. It depends on metallicity, rotation rate, magnetic field strength, mass loss history, and whether the star has a binary companion. Some stars in the intermediate range might explode in some configurations and fail in others. The outcome is not determined by mass alone, but by a complex interplay of factors that researchers are still working to untangle. Recent three-dimensional simulations have also revealed a mechanism that complicates the picture further. In some models, the standing accretion shock develops a large-scale oscillation called the standing accretion shock instability, or SASI. This instability causes the shock to slosh back and forth, alternately expanding in one direction while contracting in another. The oscillation can help trigger explosion by channeling energy into specific directions, creating conditions for the shock to break through the infalling material. In other models, the SASI competes with neutrino-driven convection, and the dominant mechanism depends on the specific properties of the progenitor star. Some simulations produce explosions primarily through convection. Others produce explosions primarily through SASI-driven dynamics. Some produce explosions through a combination of both. The diversity of mechanisms may explain the diversity of observed supernovae, which vary enormously in brightness, duration, and the amount of radioactive nickel they produce. The observed diversity is not just an academic note. It has been confirmed by real supernovae that refuse to fit neatly into standard categories. In April 2026, observations of a peculiar core collapse supernova, designated SN 2024 ABFL, revealed a Type IIP event with an unusually long plateau lasting approximately 110 days, abnormally low expansion velocities of roughly 1200 km per second at 50 days after explosion, and an exceptionally small mass of synthesized nickel-56. These properties indicate a very low-mass core collapse origin, possibly from a star just barely massive enough to undergo core collapse at all. The supernova was dim, slow, and weak compared to typical events, demonstrating that core collapse supernovae occupy a vast spectrum of violence. Some are among the most powerful explosions in the cosmos. Others are barely explosions at all, marginal events where the shock just barely manages to revive and expel the outer layers with minimal energy. This spectrum stretches from the faintest, weakest explosions at one end to the most energetic hypernovae and gamma-ray bursts at the other, with failed supernovae lurking at the extreme end where the explosion never materializes. The physics governing where a particular star falls on this spectrum is among the most active and contested research areas in modern astrophysics. But let us return to the star that does explode. The shock has revived. Neutrino heating, convective instabilities, and possibly SASI oscillations have conspired to push the shock wave back into motion. It begins accelerating outward through the outer core. It reaches the base of the silicon-burning shell, then the oxygen shell, then the carbon shell. Each successive layer offers less resistance as the density drops. The shock picks up speed. Material behind the shock is heated to temperatures where nuclear reactions reignite, adding energy to the explosion through what physicists call explosive nucleosynthesis. New elements are forged in the passage of the shockwave itself: silicon, sulfur, argon, calcium, titanium, iron, and nickel. These are not the products of millions of years of patient stellar burning. These are elements born in the violence of the explosion, synthesized in seconds as the shock tears through the star's layered structure. The shock reaches the hydrogen envelope, the outermost layers of the star, still unaware that the core collapsed minutes or hours ago, are suddenly struck by a wall of energy moving at tens of thousands of kilometers per second. The envelope is accelerated outward. The star begins to brighten as the shock reaches the surface. Photons trapped behind the shock flood outward. The supernova becomes visible. Within hours, the dying star becomes one of the brightest objects in its galaxy. Within days, it radiates more visible energy than the combined output of 100 billion ordinary suns. The light curve rises toward a peak that may persist for weeks before gradually declining as the expanding debris thins and cools. The explosion has expelled most of the star's mass into space at velocities of thousands to tens of thousands of kilometers per second. The material that took millions of years to assemble is now expanding into the interstellar medium, carrying with it a cargo of elements that will shape the next generation of stars and worlds. Behind the expanding debris, at the center of the explosion, something remains. Something small, something impossibly dense. Something so strange that its mere existence bends the rules of how we think about matter, gravity, and the structure of the universe. The explosion left a scar, and what fills that scar will determine whether the death of this star echoes across billions of years, or whether the remnant sits in silent darkness, warping space around itself, swallowing light, and remembering nothing. The shock wave reaches the surface of the star, and what happens next is the most luminous event the universe regularly produces. The photons that have been trapped behind the advancing shock wall, compressed and superheated as the blast tore through layer after layer of stellar material, suddenly find open space. They flood outward. The surface of the dying star brightens so rapidly that within hours the object transforms from an ordinary point of light into something that can outshine every other star in its host galaxy combined. A single exploding star, a speck of matter in a galaxy containing hundreds of billions of suns, momentarily produces more visible light than all of those suns put together. The peak luminosity of a typical core collapse supernova reaches roughly 1 billion times the brightness of our sun. Some particularly energetic events exceed even that. But the light, as spectacular as it appears, is a sideshow. The visible photons that make the supernova so dramatic to observers on distant worlds represent less than 1% of the total energy released in the explosion. The vast majority of the energy, roughly 99%, is carried away by particles that no human eye can see and no conventional telescope can detect. Neutrinos, the same ghostly particles produced during electron capture in the collapsing core, now stream outward in a torrent so intense it defies comprehension. The proto-neutron star at the center of the explosion radiates approximately 3 times 10 to the 53 ergs of energy in neutrinos over a period of roughly 10 seconds. To put that figure in some kind of context, the total energy output of our sun over its entire 10 billion year lifetime amounts to roughly 1.2 times 10 to the 51 ergs. The dying star releases more than 200 times that amount in neutrinos alone in 10 seconds. The energy budget of the supernova is dominated so completely by neutrino emission that the kinetic energy of the expanding debris, the energy that tears the star apart and flings its material across light years of space, amounts to roughly 1% of the neutrino energy. And the luminous energy, the light that makes the supernova visible across cosmological distances, is roughly 1% of the kinetic energy. The spectacular flash that astronomers observe is a rounding error in the total energy accounting of the event. This is why neutrino detection is so critical to supernova science. On February 23, 1987, 3 neutrino detectors on Earth recorded a total of approximately 25 neutrino events within a window of roughly 13 seconds. Those 25 particles had traveled 160,000 light-years from the Large Magellanic Cloud, a satellite galaxy of the Milky Way, where a blue supergiant star had just undergone core collapse. The event, designated supernova 1987A, became the most important supernova in the history of modern astronomy. It was the first supernova visible to the naked eye since Kepler's supernova in 1604. It was the first supernova from which neutrinos were directly detected. And those 25 neutrinos confirmed a prediction that theorists had been making for decades. The energy released in a core collapse is overwhelmingly carried by neutrinos, not by light. 25 particles. That was enough to validate an entire theoretical framework. The reason so few were detected despite the titanic flux streaming from the explosion is that neutrinos interact with matter so weakly that even a detector containing thousands of tons of water or scintillator fluid will capture only a handful from an event occurring in a neighboring galaxy. The roughly 10 to the 58 neutrinos produced by supernova 1987 are passed through the Earth almost entirely unnoticed. They streamed through the planet, through the detectors, through every living organism on the surface, and continued outward into space without slowing down. Of the incomprehensible flood, 25 happened to interact with atomic nuclei inside the detectors at precisely the right moment. Today, neutrino detectors are far more capable. Super Kamiokande in Japan, Ice Cube at the South Pole, and the deep underground neutrino experiment currently under construction in the United States could collectively detect thousands of neutrino events from a supernova occurring within our own galaxy. A network called the Supernova Early Warning System, or SNEWS, links these detectors together so that a neutrino burst detection can trigger automated alerts to observatories worldwide within minutes. Because neutrinos escape the collapsing core hours before the shockwave reaches the stellar surface and produces visible light, a galactic supernova would announce itself in neutrinos first. Astronomers would know a star was exploding before the light arrived. They would have time to point every available telescope at the correct location in the sky and capture the very first photons emerging from the blast. This has never happened in the era of modern astronomy. When it does, the scientific return will be extraordinary. The expanding material ejected by the explosion races outward at velocities ranging from a few thousand to more than 30,000 kilometers per second, depending on the layer and the energy of the blast. The outermost hydrogen envelope moves fastest, having been accelerated through the largest distance by the shock. Deeper layers containing heavier elements move slower but carry more mass. The ejected material expands into the surrounding interstellar medium, sweeping up gas and dust and compressing it into a shell of shocked, heated material. Over time, this expanding debris forms a structure visible to telescopes across the electromagnetic spectrum, a supernova remnant. Some of these remnants are among the most visually spectacular objects in the sky. The Crab Nebula in the constellation Taurus is the remnant of a supernova observed by Chinese and Japanese astronomers in the year 1054. Nearly 1,000 years later, the debris field spans roughly 11 light-years and continues expanding at approximately 1,500 kilometers per second. At its center sits a pulsar, a rapidly spinning neutron star that rotates 30 times per second, sweeping beams of radiation through space with clockwork precision. The pulsar's rotational energy powers the nebula, driving a wind of charged particles that illuminates the expanding gas and creates the intricate filamentary structure visible in modern images. Cassiopeia A, located roughly 11,000 light-years away, is the remnant of a supernova that likely occurred around 1680, though no confirmed historical observation of the explosion exists. The remnant has been studied extensively across every wavelength from radio to X-ray, revealing a complex three-dimensional structure of expanding shells, knots of heavy elements, and shock-heated gas. X-ray observations from the Chandra Space Telescope mapped the distribution of silicon, sulfur, argon, calcium, and iron throughout the remnant showing that the explosion scattered these elements in clumps and filaments rather than in a smooth, uniform shell. The asymmetry visible in Cassiopeia A confirms what simulations predict. The explosion was not a neat, spherical blast, but a chaotic, turbulent eruption that launched different elements in different directions at different velocities. The details revealed by modern observations of these remnants are extraordinary. In Cassiopeia A, the Chandra X-ray Observatory identified knots of nearly pure iron moving at thousands of kilometers per second, ejected from the deepest layers of the exploded star. These iron-rich clumps were launched outward past lighter elements like silicon and sulfur that originated in shells above the iron core, meaning the explosion physically inverted portions of the star's layered structure. Material from the interior overtook material from the exterior, a process that only occurs in violent asymmetric explosions driven by turbulent convection and hydrodynamic instabilities. The star was not just blown apart, it was turned partially inside out. The Vela supernova remnant, located roughly 800 light-years from Earth, offers another window into the aftermath. This remnant is roughly 11,000 years old and spans nearly 8 degrees on the sky, stretching roughly 16 times wider than the apparent diameter of the full moon. The expanding shell of shocked gas has swept up so much interstellar material that it has become a major structural feature of the local interstellar medium. X-ray observations reveal a complex network of filaments, sheets, and shrapnel fragments expanding at different velocities, each one a fossil record of the explosion's hydrodynamic structure. At the center of the Vela remnant sits a pulsar spinning roughly 11 times per second, its beams sweeping through the debris like a lighthouse illuminating a shipwreck. The Tycho supernova remnant, named after the Danish astronomer Tycho Brahe, who observed the original explosion in 1572, is the remnant of a different kind of supernova entirely. Tycho was a type year event, produced not by the core collapse of a massive star, but by the thermonuclear detonation of a white dwarf in a binary system. In a type year supernova, a white dwarf, the dense remnant of a low-mass star that died quietly, accumulates matter from a companion star until it approaches the Chandrasekhar limit. The entire white dwarf then ignites in a runaway thermonuclear explosion that destroys the star completely, leaving no compact remnant at all, no neutron star, no black hole, just an expanding cloud of debris rich in iron group elements, particularly nickel-56. Type year supernovae are important to this story, not because they represent the core collapse mechanism we have been examining, but because they illustrate that nature has more than one way to destroy a star. The universe has engineered multiple pathways to stellar annihilation, each producing different elements in different proportions and scattering them through different regions of interstellar space. The distinction matters chemically. Core collapse supernovae produce the majority of the universe's oxygen, carbon, neon, magnesium, and silicon, the elements that dominate rocky planetary material. Type Ia supernovae produce a disproportionately large fraction of the universe's iron, roughly half or more of the total cosmic iron inventory. The iron in your blood may well have originated in a Type Ia explosion rather than a core collapse event. Different types of stellar death feed different elements into the cosmic supply chain, and the full chemical richness of the universe depends on both mechanisms operating over billions of years. Each supernova remnant is a time capsule. The ratios of elements in its debris encode information about the progenitor star's mass, its metallicity, its rotation rate, and the physics of the explosion itself. By studying remnants of different ages and types scattered across the galaxy, astronomers reconstruct the nucleosynthetic history of the Milky Way, tracing how the chemical composition of the interstellar medium has evolved from the nearly pristine hydrogen and helium of the early universe to the element-rich mixture from which our solar system formed. These remnants are not just beautiful relics of past violence, they are active participants in the ongoing evolution of the galaxy. The expanding shockwave from a supernova remnant compresses the interstellar medium ahead of it, triggering the collapse of gas clouds that might otherwise have remained stable for millions of years. This compression can initiate the formation of new stars. There is strong evidence that our own solar system formed from a molecular cloud that was disturbed by a nearby supernova roughly 4.5 billion years ago. Isotopic signatures in primitive meteorites, particularly the presence of short-lived radioactive isotopes like aluminum-26 and iron-60, point to a supernova injection event shortly before or during the formation of the solar nebula. The shock wave from a dying star may have been the trigger that caused our own sun to ignite. But before we follow those elements into the next generation, we need to examine what the explosion left behind at the center, because the remnant at the core of a supernova is one of the strangest objects in the universe. When the core of a massive star collapses and the shock wave successfully ejects the outer layers, the proto-neutron star left behind at the center cools and contracts into a stable configuration over the following minutes and hours. The result is neutron stars, objects roughly 20 kilometers across containing more mass than the Sun, compressed to densities exceeding that of an atomic nucleus throughout their entire volume. The density inside a neutron star exceeds the density of an atomic nucleus throughout its entire volume. At its core, conditions may become so extreme that nuclear matter undergoes phase transitions into exotic states that physicists have never directly observed, potentially including quark matter, where the individual quarks that normally remain confined inside protons and neutrons are liberated into a degenerate soup. The surface gravity of a neutron star is roughly 200 billion times the gravitational acceleration at Earth's surface. If you could somehow stand on a neutron star, which you could not because the gravity would compress you to a film of atoms thinner than a sheet of paper, an object dropped from a height of 1 meter would strike the surface at roughly 7 million kilometers per hour. Light leaving the surface is measurably bent by the curvature of space-time, so strong that a neutron star with a radius of 10 kilometers allows an observer to see roughly 75% of the entire surface at once. The star's gravity literally curves light around its own body, revealing portions of the far side that would be geometrically hidden on any less extreme object. Neutron stars also rotate. The conservation of angular momentum guarantees this. A massive stellar core that rotated once every few weeks or months is compressed into a body 100,000 times smaller in radius. The rotation rate increases by the square of the compression factor. What was a lazy stellar spin becomes a frenzied rotation of many times per second. The fastest known neutron star, PSRJ 1748, 2446 AD, rotates 716 times per second. Its equator moves at roughly 15 to 20% of the speed of light, depending on the assumed radius. These rapidly rotating neutron stars often possess extraordinarily powerful magnetic fields, trillions of times stronger than Earth's magnetic field, which channel beams of electromagnetic radiation along the magnetic poles. As the star spins, these beams sweep through space. If a beam happens to cross Earth's line of sight, we detect a regular pulse of radiation, a pulsar. The existence of neutron stars was predicted, theoretically, in 1934 by Walter Bade and Fritz Zwicky, who proposed that supernovae represent the transition of ordinary stars into neutron stars. The prediction was confirmed 33 years later, when Jocelyn Bell Burnell detected the first pulsar in 1967 while working on her doctoral thesis at Cambridge. The discovery of pulsars and their identification as rotating neutron stars represented one of the most dramatic confirmations of theoretical prediction in the history of astrophysics. But for supernova 1987A, the most intensely studied supernova since the invention of the telescope, the expected neutron star remained hidden for decades. The neutrino detection confirmed that a compact object had formed during the collapse. The duration of the neutrino burst, roughly 10 seconds, was consistent with a neutron star cooling through neutrino emission, rather than the abrupt cutoff expected from black hole formation. Theoretical models predicted a neutron star, but no one could see it. The expanding debris from the explosion, rich in dust and heavy elements, obscured the center of the remnant so effectively that no direct detection of the compact object was possible at optical, infrared, or X-ray wavelengths for over 3 decades. Then came the James Webb Space Telescope. In observations taken in July 2022, a team led by Claes Fransson of Stockholm University used JWST's infrared spectroscopic instruments to peer through the dust enshrouding the remnant's center. They detected narrow emission lines from highly ionized argon and sulfur, originating from a spatially unresolved source near the center of the expanding ejecta. The ionization of these elements requires a source of high-energy photons, ultraviolet or X-ray radiation, emanating from something compact and energetic at the heart of the remnant. Photoionization models showed that the observed line ratios were consistent with ionization by a cooling neutron star or a pulsar wind nebula. The emission lines were also blue-shifted relative to the supernova's rest frame, suggesting the compact object is moving toward us, a potential signature of a neutron star natal kick received during the asymmetric explosion. This result, published in the journal Science in 2024, represented the first direct evidence for emission from a newborn compact object in any observed supernova. For 37 years, astronomers had searched. Fransson himself had published simulations in 1992, predicting how a neutron star's radiation would excite emission lines in the surrounding ejecta. Only with JWST's unprecedented infrared sensitivity and spectral resolution did the detection become possible. The result strongly favors a neutron star rather than a black hole, confirming the prediction made by those 25 neutrinos detected on Earth in February 1987. Supernova, 1987. A produced a neutron star. It took nearly 4 decades of technological advancement to prove it. Not all core collapse supernovae leave neutron stars. When the collapsing core is too massive, exceeding roughly 2 to 2.2 solar masses, even neutron degeneracy pressure and the repulsive strong nuclear force cannot halt the collapse. The core passes through the neutron star stage and continues falling inward until it crosses its own Schwarzschild radius, the boundary beyond which the escape velocity exceeds the speed of light. A black hole forms. The event horizon seals off the interior from the observable universe. No light, no matter, no information can escape. The remnant is not an object in the conventional sense. It is a region of space-time where gravity is won absolutely and permanently. Stellar mass black holes formed through core collapse typically have masses ranging from roughly 5 to perhaps 30 solar masses, depending on how much material falls back after the explosion or how much was lost through stellar winds during the star's lifetime. Observations from the LIGO and Virgo gravitational wave detectors have now catalogued more than 100 mergers involving stellar mass black holes, confirming that these objects exist in abundance throughout the universe. Some of those black holes may have formed through successful supernovae, where the fallback of material pushed the neutron star over its mass limit. Others may have formed through failed supernovae, where no explosion occurred at all, as in the case of M31, 2014, D-S1. The distinction between neutron star and black hole formation is not merely academic. It determines what happens to the surrounding environment. A neutron star, particularly a rapidly rotating pulsar, can inject enormous amounts of energy into its surroundings for thousands of years after the explosion. The Crab Nebula's ongoing luminosity is powered entirely by the rotational energy of its central pulsar. Without that continuous energy input, the nebula would have faded long ago. Pulsars also produce relativistic winds of electrons and positrons that create pulsar wind nebulae, structures that can extend across light years and glow in X-ray and radio wavelengths. A black hole, by contrast, is silent unless matter falls into it. A stellar mass black hole sitting alone in interstellar space produces no radiation, no wind, no detectable emission of any kind. It reveals itself only through its gravitational effects on nearby matter or passing light. The universe could be populated with millions of silent black holes formed through failed supernovae, drifting unseen through the galaxy, detectable only if they happen to pass in front of a background star and briefly magnify its light through gravitational microlensing. But whether the remnant is a neutron star or a black hole, the debris field expanding outward from the explosion is the same, and it is this debris that carries the real payload. the supernova has ejected several solar masses of material into space. This material is not uniform hydrogen and helium. It is enriched with heavy elements forged during the star's lifetime and during the explosion itself. The layered onion structure of the pre-collapsed star has been shattered, mixed, and expelled. Elements that were neatly separated into concentric shells inside the star are now jumbled together in expanding filaments and clumps. The debris contains enormous quantities of oxygen, the most abundant element produced by core-collapse supernovae. It contains carbon, neon, magnesium, silicon, sulfur, calcium, and iron, all synthesized during the star's sequential burning phases. It contains radioactive nickel-56, produced during explosive silicon burning as the shockwave tore through the star. This isotope is critically important because its radioactive decay, first into cobalt-56 and then into stable iron-56, powers the visible light curve of the supernova for months after the initial explosion. The characteristic decline in brightness observed in Type II supernovae follows the decay timescale of nickel-56 almost exactly. Without this radioactive heating, the expanding debris would cool and fade far more quickly. But the explosion also produces elements through a process far more violent than anything that occurred during the star's life. As the shock wave tears through the outer core and the neutrino-heated ejector expand outward, conditions arise in which atomic nuclei are bombarded with neutrons at rates so extreme that they capture multiple neutrons before having time to undergo radioactive decay. This is the rapid neutron capture process, known as the R process, one of the fundamental mechanisms by which nature builds the heaviest elements on the periodic table. In the intense neutron flux of the supernova's innermost ejector, seed nuclei rapidly climb the chart of isotopes, adding neutrons and occasionally decaying back towards stability, creating elements far heavier than iron that could never be produced through normal stellar fusion. The role of core-collapse supernovae in reprocessed nucleosynthesis remains one of the most actively debated questions in nuclear astrophysics. For decades, supernovae were assumed to be the dominant source of all R-process elements, from strontium and barium up through gold, platinum, and uranium. But as computer simulations of supernovae improved, they revealed that the conditions in most core collapse events may not produce a sufficiently intense neutron flux to create the heaviest R-process elements. The neutrino-driven wind from the proto-neutron star, once considered the primary R-process site, turns out to be marginally neutron-rich in many simulations, producing lighter R-process elements like strontium and zirconium, but struggling to reach the heaviest peaks of the R-process abundance pattern. In 2017, the detection of gravitational waves from a neutron-star merger designated GW170817, followed by the observation of a kilonova, provided dramatic evidence that neutron-star collisions are prolific R-process factories. The extreme neutron-rich material ejected during the merger produced spectroscopic signatures consistent with the creation of heavy R-process elements, including lanthanides and possibly actinides. This observation shifted the scientific consensus. Many astrophysicists now believe that neutron-star mergers are the dominant source of the heaviest R-process elements, while core-collapse supernovae contribute primarily to the lighter R-process elements and dominate the production of intermediate mass elements between oxygen and the iron group. The debate carries real scientific tension because both candidate sources have strengths and weaknesses that refuse to resolve into a clean answer. Neutron-star mergers produce spectacularly neutron-rich ejecta. The material thrown off during the collision of two neutron stars contains so many free neutrons per seed nucleus that the R process can climb the periodic table all the way to uranium and beyond, producing the heaviest naturally occurring elements with an efficiency that no supernova simulation has been able to match. The kilonova that followed GW170817 glowed with the characteristic red color of lanthanide-rich ejecta, elements in the middle of the periodic table that require intense neutron bombardment to create. The spectroscopic signatures were unmistakable. Neutron-star mergers make heavy R-process elements, and they make them abundantly. But neutron-star mergers have a timing problem. Two neutron stars can only merge after both have been produced by separate supernovae in a binary system, and then the system must spiral inward through gravitational wave emission over a timescale that can range from millions to billions of years. This delay means that neutron star mergers contribute their elements to the interstellar medium on a very different schedule than supernovae. Some of the oldest, most metal-poor stars in the Milky Way's halo, stars that formed when the galaxy was young and very few stellar generations had occurred, have already shown robust R-process abundance patterns, including heavy elements like europium and barium. If neutron star mergers take hundreds of millions or billions of years to occur after the supernovae that created them, how did these elements appear so early in galactic history? The timescale seems too short for mergers to be the sole explanation. Core collapse supernovae, on the other hand, occur almost immediately after a massive star forms, on timescales of just a few million years. They could enrich the early galaxy with R-process material far more quickly than mergers, but standard simulations of core collapse supernovae struggle to produce the extreme neutron-rich conditions needed for the heaviest R-process elements. The neutrino-driven wind that streams off the proto-neutron star after the explosion tends to be only marginally neutron-rich, and in many simulations it actually becomes proton-rich, shutting down the reprocess entirely beyond the lightest heavy elements. This impasse has driven researchers to explore whether specific rare subtypes of core collapse events might fill the gap. Magnetorotational supernovae, explosions of rapidly rotating, strongly magnetized massive stars, can produce jet-driven outflows with extremely neutron-rich conditions that are favorable for heavy R-process nucleosynthesis. These events are rare, perhaps 1 in every 100 or even 1 in every 1,000 core collapse supernovae, but if each one produces a large mass of heavy R-process elements, their cumulative contribution over galactic history could be significant. Similarly, collapsars, the engine behind long-duration gamma-ray bursts where a massive star's core collapses directly into a black hole surrounded by an accretion disk, can launch neutron-rich outflows from the disk that produce heavy elements. The diversity of possible R-process sites reflects the diversity of ways massive stars can die, and the relative contribution of each site remains one of the most actively pursued questions in nuclear astrophysics. What is clear is that the universe does not rely on a single mechanism to build its heaviest elements. The periodic table beyond iron was constructed by multiple processes operating in multiple environments over billions of years. Supernovae, neutron star mergers, and possibly exotic subtypes of stellar explosions all contributed. The gold in a wedding ring may trace its origin to a neutron star collision that occurred billions of years ago in a completely different region of the galaxy. The strontium in fireworks may have been produced in the neutrino-driven wind of a core collapse supernova. The barium in medical imaging contrast may have formed in a magnetorotational jet. Each element carries a history written in nuclear physics, and decoding that history requires understanding not just one type of stellar death, but all of them. The picture is not settled. Certain rare types of core collapse supernovae, particularly those involving rapidly rotating, highly magnetized progenitors that produce jets and extreme conditions, may create conditions favorable for heavy R-process nucleosynthesis. Magnetorotational supernovae and collapsers, the engines behind long-duration gamma-ray bursts, remain candidate sites for heavy element production. The contribution of different astrophysical sources to the cosmic inventory of heavy elements is a question that depends on the frequency of each type of event, the mass of material ejected, and the neutron richness of that material. These are quantities that observations and simulations are still working to pin down. What is not debated is the central role of core collapse supernovae in producing and distributing the intermediate mass elements that form the bulk of rocky planetary material. Oxygen, carbon, silicon, magnesium, sulfur, calcium, iron. These are the elements that constitute Earth's crust, mantle, and core. These are the elements that form the silicate minerals in every rocky planet, in every star system in the galaxy. Without core collapse supernovae, these elements would remain locked inside the stars that produced them, inaccessible and useless. The explosion is the delivery mechanism. It is the act that transforms private stellar chemistry into public cosmic resources, scattering the building blocks of worlds across light years of interstellar space. The debris field from a supernova does not simply dissipate into uniform nothingness. It expands, cools, and eventually merges with the surrounding interstellar medium. Over hundreds of thousands of years, the remnant fades from visibility as it slows and disperses. But the elements it carried remain. They mix into molecular clouds, vast reservoirs of cold gas and dust where gravity will eventually begin pulling material together again. Those clouds, enriched with heavy elements from generations of stellar explosions, will fragment and collapse into new protostars surrounded by disks of gas and dust. Those disks will coalesce into planets. Those planets will incorporate the heavy elements delivered by supernovae into their crusts, their oceans, and their atmospheres. The expanding remnant also carries kinetic energy and momentum that stir the interstellar medium, driving turbulence on scales of tens of light years. This turbulence helps regulate star formation throughout the galaxy, compressing some regions to trigger collapse while dispersing others to suppress it. Supernovae are not passive contributors to galactic evolution. They are active agents that shape the structure, chemistry, and star formation rate of their host galaxies over billions of years. And in some cases, the expanding shock wave from a supernova does not merely stir the surrounding gas, it directly triggers the formation of a new generation of stars. The compressed shell of swept-up material ahead of the remnant can become gravitationally unstable, fragmenting into dense clumps that collapse under their own weight. These clumps become stellar nurseries. New stars ignite. New planetary systems form. New worlds take shape, built from material that includes atoms forged in the interior of the star that just died and delivered to this location by the violence of its explosion. This is not speculation. This is observed. Star-forming regions throughout the galaxy show evidence of supernova-triggered collapse. The distribution of short-lived radioactive isotopes in the solar system's oldest meteorites places a supernova within a few light years of the cloud that formed our Sun, within a few million years of the solar system's birth. The timing and proximity are consistent with a scenario in which a massive star exploded nearby, and the shock wave from that explosion compressed the molecular cloud that became our solar nebula. The debris is still expanding. The elements are still being delivered. Somewhere in the galaxy, right now, a supernova remnant is colliding with a molecular cloud, compressing it, enriching it, and setting the stage for new stars to form. The death of one star becomes the birth announcement for others. The chain is continuous. It has been running for over 13 billion years since the first massive stars formed and died in the young universe. Every generation of stars is built from the ashes of the previous generation, and every generation contributes new elements to the cosmic inventory. But the full weight of what this means, the real shock hidden inside the violence, is something we have not yet confronted directly. We have watched the star collapse. We have seen the shock revive. We have followed the debris as it expands into space. We know what the explosion leaves behind and what it scatters, but we have not yet drawn the line that connects all of this to you, to the ground beneath your feet, to the iron in your blood and the calcium in your bones, to the oxygen entering your lungs as you hear these words. That line exists. It is not poetic. It is not metaphorical. It is physical, measurable, and confirmed by every isotopic analysis ever performed on the material in our solar system. The death of a star is not the end of a story. It is the middle of one, and what comes next is where destruction becomes creation. Every atom of oxygen you have ever breathed was manufactured inside a star that no longer exists. Every atom of calcium that gives your skeleton its rigidity was assembled in a stellar core that collapsed billions of years before the Earth formed. The iron carrying oxygen through your bloodstream at this exact moment was forged in a nuclear furnace that burned for millions of years, built an element it could not use, and then died in an explosion so violent it briefly outshone everything else in its galaxy. These are not metaphors. These are not poetic comparisons designed to make you feel connected to the cosmos. These are literal, confirmed, measurable facts of nuclear physics and isotopic chemistry. You are, in the most precise scientific sense available, constructed from the debris of dead stars. This realization has been building throughout this entire story. We watched a massive star burn through fuel after fuel in a desperate race against gravity. We followed the iron core as it collapsed at a quarter of the speed of light. We saw the shock wave stall, revive, and tear the star apart. We tracked the expanding debris as it scattered elements across light years of interstellar space. Now we need to confront what that scattering actually means. Because the supernova did not merely destroy a star, it performed one of the universe's most essential functions. It took elements that were locked away inside a stellar interior, elements that would have been permanently inaccessible to the rest of the cosmos, and it distributed them into the raw material from which new stars, new planets, and new living things would eventually be built. To understand the full weight of this claim, consider what the universe looked like before the first stars died. In the first few minutes after the Big Bang, primordial nucleosynthesis produced the lightest elements: hydrogen, helium, and trace amounts of lithium. That was all. The periodic table ended at element number 3. No carbon, no oxygen, no nitrogen, no silicon, no iron, no calcium, nothing that could form a rock, a mineral, a molecule of water, a strand of DNA. The early universe was chemically barren. It contained the fuel for stars, but none of the raw materials for planets or life. Everything heavier than lithium was produced later, inside stars. This is the central insight of stellar nucleosynthesis. The theoretical framework developed by Fred Hoyle and refined by Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Hoyle in their landmark 1957 paper, universally known as B²FH. That paper demonstrated that the abundances of elements observed in the universe could be explained entirely by nuclear reactions occurring inside stars of various masses at various stages of their evolution. The universe did not begin with a full periodic table. It built one, element by element, generation by generation, inside the nuclear furnaces of successive stellar populations. The first generation of stars, called Population 3 stars, formed from pure hydrogen and helium. They contained no heavy elements because none existed yet. These primordial stars were likely very massive, hundreds of times the mass of our Sun, and they burned through their fuel quickly. When they exploded, they produced the first batch of heavy elements and scattered them into the surrounding gas. The next generation of stars formed from gas that was slightly enriched with these elements. They lived, fused new elements in their cores, exploded, and scattered their products into the interstellar medium. Each generation enriched the cosmic reservoir a little further. Each generation added new elements to the inventory. Over billions of years and billions of stellar lifetimes, the chemical complexity of the universe increased steadily from a simple mixture of hydrogen and helium to the rich diversity of elements we observe today. This process is not uniform. Different elements are produced by different types of stars at different stages of their evolution. The lightest elements beyond lithium, carbon, and nitrogen are produced primarily in intermediate mass stars through hydrogen and helium burning and dispersed through stellar winds and planetary nebula ejection. These stars do not explode. They shed their outer layers gently. But the heavier elements, from oxygen through the iron group, are produced overwhelmingly in massive stars and released almost exclusively through core collapse supernovae. Without explosions, these elements remain trapped. Consider oxygen, the third most abundant element in the universe by mass and the most abundant element in Earth's crust. Oxygen is synthesized primarily during helium burning in massive stars, where helium nuclei fuse to form carbon, and then carbon captures an additional helium nucleus to become oxygen. Some oxygen is also produced during neon and carbon burning, but all of this oxygen sits deep inside the star's layered structure, inaccessible to the rest of the universe. It cannot leak out. It cannot diffuse through the star's outer layers. Stellar winds from massive stars carry away some surface material, but the oxygen produced in the core never reaches the surface during the star's lifetime. The only mechanism that liberates this oxygen is the supernova. When the shock wave tears through the oxygen-rich shell, it heats the material, accelerates it to thousands of kilometers per second, and expels it into interstellar space. Without that explosion, the oxygen remains permanently entombed. The same logic applies to silicon, the element that gives rocky planets their fundamental mineral structure. Silicon is produced during oxygen burning and explosive nucleosynthesis as the shock wave passes through the silicon and oxygen shells. Magnesium, synthesized during carbon and neon burning, follows the same path. Sulfur and calcium, products of oxygen and silicon burning, are ejected only through the violence of the explosion. Iron itself, the element whose accumulation triggered the collapse in the first place, is scattered into space, along with the radioactive nickel-56, whose decay powers the supernova's visible light for months. Each of these elements was created through a specific nuclear reaction at a specific temperature and pressure inside a specific layer of a dying star, and each of them was delivered to the interstellar medium through a specific physical process. The passage of a shock wave through stellar material at velocities exceeding 10,000 kilometers per second. The precision of this chain, from nuclear physics to fluid dynamics to interstellar chemistry, is remarkable. The universe does not have a simpler way to build these elements. There is no shortcut. You cannot make oxygen without first making carbon. You cannot make silicon without first making oxygen. You cannot make iron without first making silicon. And you cannot get any of them out of the star without blowing it apart. Now follow those elements forward in time. The supernova remnant expands for hundreds of thousands of years, gradually slowing as it sweeps up interstellar gas. The heavy elements it carries mix into the surrounding medium. Over millions of years, turbulent motions in the interstellar medium blend the supernova ejector with ambient hydrogen and helium, creating molecular clouds enriched with heavy elements. These clouds are cold, dense, and gravitationally unstable. Perturbations from passing spiral arms, nearby supernovae, or collisions between clouds trigger gravitational collapse. Fragments of the cloud begin contracting. Each fragment heats up as gravitational energy converts to thermal energy. When the central temperature reaches roughly 10 million degrees, hydrogen fusion ignites. A new star is born. The material left over from the collapsing fragment does not all fall into the new star. Conservation of angular momentum flattens some of it into a rotating disk of gas and dust surrounding the young protostar. This is a protoplanetary disk, and it is the birthplace of planets. Within this disk, tiny dust grains composed of silicates, oxides, and metallic iron, all products of previous supernovae, collide and stick together. These aggregates grow from microscopic particles to pebble-sized bodies to kilometre-scale planetesimals over a few million years. Gravitational interactions between planetesimals drive further growth through collisions and mergers. Rocky protoplanets emerge. Gas giants form in the outer disk, where temperatures are low enough for volatile compounds to condense. Within 10 to 50 million years, a planetary system takes shape around the new star. Every atom of silicon in the rocky planets of that system was produced inside a massive star and delivered by a supernova. Every atom of iron in the cores of those planets followed the same path. The oxygen bound into silicate minerals, the magnesium in olivine crystals, the calcium in plagioclase, feldspar, all of it traces back to stellar interiors and supernova explosions. The planets are not made from primordial material. They are made from recycled stellar ash. The ground beneath your feet is the processed remains of stars that lived and died before the sun existed. Our own solar system fits this pattern precisely. Isotopic analysis of the oldest solid objects in the solar system, calcium-aluminum-rich inclusions found in primitive meteorites called chondrites, reveals the fingerprints of multiple nucleosynthetic sources. The relative abundances of different isotopes of elements like oxygen, titanium, chromium, and nickel vary slightly between different meteoritic components, indicating that the solar nebula was not perfectly mixed. It contained material from several distinct stellar sources, each contributing its own isotopic signature. The solar system is not the product of a single supernova. It is the product of billions of years of galactic chemical evolution, with contributions from dozens or hundreds of individual stellar sources blended together in the molecular cloud that became our Sun. But the evidence for a specific supernova contribution in the final moments before solar system formation is compelling. The presence of aluminum-26 in the earliest solar system solids requires a source of this short-lived radioactive isotope with a half-life of only 717,000 years. Aluminum-26 is produced in the carbon and neon-burning shells of massive stars and ejected during supernovae. Its presence in the solar system's oldest materials means that a supernova must have occurred within a few million years and a few light years of the collapsing solar nebula. Similarly, iron-60, another short-lived isotope produced in supernovae with a half-life of roughly 2.6 million years, has been detected in early solar system materials. These isotopes could not have survived from a distant or ancient source. They must have been freshly injected by a nearby explosion shortly before or during the formation of the Sun. The scenario that emerges is striking. A massive star, perhaps 20 or 30 times the mass of our Sun, lived and died in the same region of the galaxy where our molecular cloud was slowly gathering material. When it exploded, the shock wave from the supernova compressed the outer layers of the cloud, triggering gravitational collapse. Simultaneously, freshly synthesized radioactive isotopes from the explosion were injected into the collapsing material. The supernova did not merely contribute raw materials to our solar system. It may have caused our solar system to form. The birth of our Sun and the death of a nearby star may have been causally connected, two events in a single chain of cosmic recycling. This chain has been running since the first generation of stars formed roughly 200 to 400 million years after the Big Bang. Those first stars produced the first heavy elements. Their explosions enriched the primordial gas. The next generation formed from that enriched material, burned through additional fuel stages made possible by the higher metallicity, and exploded in turn, further enriching the interstellar medium. Generation after generation, the heavy element content of the galaxy increased. Astronomers can trace this enrichment history by observing stars of different ages and measuring their chemical compositions. The oldest stars in the Milky Way's halo, formed when the galaxy was young, contain very few heavy elements, sometimes less than 1,000th the solar abundance. Younger stars in the disk, formed more recently from more enriched material, contain progressively higher proportions of heavy elements. Our Sun, formed roughly 4.5 billion years ago, has a metallicity typical of its generation, reflecting billions of years of chemical enrichment by successive stellar populations. This generational structure means that every atom heavier than hydrogen and helium in your body has been through at least one star. Most have been through several. A carbon atom in your DNA might have been synthesized in a red giant star 7 billion years ago, ejected in a planetary nebula, incorporated into a molecular cloud, swept up by a supernova shock wave from a different star, mixed into a new cloud, and finally incorporated into the solar nebula that formed our Sun and planets. An iron atom in your blood might have been produced in a core collapse supernova 9 billion years ago, spent billions of years drifting through interstellar space, been incorporated into a star that later ejected it through stellar winds, and finally arrived in the molecular cloud that became our solar system. The history encoded in every atom in your body spans billions of years and multiple stellar lifetimes. This is the cosmic recycling loop. Stars form from interstellar gas. They fuse light elements into heavy ones during their lifetimes. They die and return enriched material to the interstellar medium, either gently through winds and planetary nebulae or violently through supernovae. New stars form from the enriched gas, incorporating the heavy elements produced by their predecessors. The cycle repeats. Each iteration increases the chemical complexity of the galaxy. Each iteration provides new raw materials for planet formation. Each iteration expands the possibilities for chemistry, mineralogy, and ultimately biology. Supernovae occupy a unique and irreplaceable position in this cycle. They are the only mechanism capable of producing and distributing the intermediate and heavy elements that constitute rocky planetary material. Stellar winds from low-mass stars contribute carbon and nitrogen, but not the heavier elements needed for planetary geology. Neutron star mergers contribute heavy R-process elements like gold and platinum, but occur too infrequently and too asymmetrically to account for the bulk composition of rocky planets. Core collapse supernovae produce the majority of the elements between oxygen and iron, the elements that dominate the mass budget of terrestrial planets, and they occur frequently enough, roughly 2 per century in a galaxy like the Milky Way, to maintain a steady flow of enriched material into the interstellar medium. Without supernovae, the universe would still contain stars, hydrogen fusion would still operate, galaxies would still form and evolve, but the chemical palette available for planet formation would be drastically impoverished. Rocky planets, as we know them, could not exist without silicon, magnesium, iron, and oxygen in sufficient quantities. Water could not form without oxygen. Organic chemistry could not proceed without carbon, nitrogen, and oxygen. The biochemistry that underlies every living organism on Earth depends on elements that were produced inside massive stars and delivered by their explosions. Life as we understand it is a downstream consequence of supernova nucleosynthesis. This connection between stellar death and biological existence is not an abstract philosophical point. It is a quantifiable physical relationship. The mass of heavy elements in the Earth, approximately 6 times 10 to the 24 kilograms, was produced by supernovae over a period of roughly 9 billion years before the solar system formed. The rate of supernova enrichment, the mixing efficiency of the interstellar medium, and the timing of molecular cloud collapse all had to align within appropriate parameters for a solar system with our chemical composition to form at the time and place it did. Change the supernova rate significantly, and you change the metallicity of the gas available for planet formation. Change the metallicity, and you change the types of planets that form, the abundance of water, and the availability of biologically essential elements. The universe did not have to produce life. Nothing in the laws of physics guarantees that nuclear fusion inside stars would produce the specific set of elements needed for complex chemistry. Nothing guarantees that those elements would be liberated from stellar interiors through explosions. Nothing guarantees that the enriched material would be incorporated into planets where liquid water could exist and organic molecules could form. The chain from stellar nucleosynthesis to biology involves dozens of steps, each governed by specific physical constants and conditions. Yet the chain exists. It operates. It has been running for over 13 billion years, and you are standing at the end of it. Every breath you take contains oxygen atoms forged in the helium-burning shell of a star that exploded before the sun existed. The phosphorus in your DNA, essential for the backbone of every genetic molecule, was synthesized during explosive neon and carbon burning as a supernova shockwave tore through a dying star. The sulfur in your amino acids was produced during oxygen burning. The potassium that drives the electrical signals in your nervous system was created during explosive oxygen burning. The zinc in the enzymes that regulate your metabolism was assembled partly through slow neutron capture during the star's late burning phases, and partly in the explosive chaos of the supernova itself, when rapidly recombining protons and neutrons forged new nuclei in the seconds after the shockwave passed. Every one of these elements was trapped inside a stellar interior until an explosion liberated it. Every one of them traveled through interstellar space for millions or billions of years before being incorporated into the molecular cloud that became our solar system. Every one of them followed a chain of physical processes, stretching from nuclear physics to stellar evolution, to supernova dynamics, to interstellar chemistry, to planetary formation, to biology. And this process is not finished. It is happening now, at this moment, across the entire galaxy. Massive stars are burning through their final fuel stages. Iron cores are growing toward the Chandrasekhar limit. Cores are collapsing. Shock waves are reviving. Stars are exploding. Debris fields are expanding into the interstellar medium, carrying cargoes of freshly synthesized elements. Molecular clouds are being compressed, enriched, and triggered into collapse. New stars are forming. New planetary systems are assembling from disks of enriched gas and dust. Somewhere in the Milky Way, right now, a planet is taking shape around a young star, and the silicon and iron and oxygen in that planet's crust were produced by a supernova that occurred millions of years ago and thousands of light years away. The chain extends forward as well as backward. Our own sun will eventually exhaust its hydrogen fuel and evolve into a red giant. It will shed its outer layers, returning some material to the interstellar medium, but because the sun is not massive enough to undergo core collapse, it will not produce a supernova. It will not forge elements heavier than carbon and oxygen. It will not scatter iron and silicon into space. The heavy elements currently locked inside Earth, the iron in its core, the silicon in its mantle, the calcium and phosphorus in every living organism on its surface, will remain bound to the solar system's remnants unless some external process disrupts them. The cosmic recycling loop requires massive stars. It requires explosions. It requires violence on a scale that dwarfs anything in human experience. This is the central paradox at the heart of this story. One of the most destructive events in the universe is also one of its most creative. A supernova obliterates a star. It releases enough energy to sterilize entire regions of interstellar space. It produces radiation and particle fluxes lethal to any unshielded biological system within tens of light years. It is an act of annihilation so complete that the star ceases to exist as a recognizable object, replaced by either a neutron star or a black hole surrounded by an expanding cloud of debris. Yet that same act of annihilation is the mechanism by which the universe produces the elements needed for rocky planets, liquid water, organic chemistry, and life. Without supernovae, the cosmos would be chemically simple, biologically sterile, and structurally monotonous. Hydrogen and helium, stars and gas forever. No planets, no mountains, no oceans, no molecules complex enough to replicate themselves. No eyes to look up at the night sky and wonder what the stars are made of. The universe needed stars to die in order for anything interesting to exist. It needed cores to collapse, shock waves to revive, and debris to scatter. It needed the precise physics of nuclear binding energies, the specific properties of the strong nuclear force, and the particular behavior of neutrinos at extreme densities to conspire in exactly the right way to produce explosions rather than silent collapses. And then it needed those explosions to occur frequently enough, over billions of years across billions of galaxies, to enrich the interstellar medium to the point where rocky planets became possible. Look up at the night sky one more time. Find any star. Consider the possibility that it might be massive enough to explode someday. Consider what that explosion would produce. Consider the elements that would be forged in its final moments and scattered across light years of space. Consider the molecular cloud that those elements might someday enrich. Consider the new star that might form from that cloud, and the planets that might coalesce around it, and the chemistry that might unfold on one of those planets if the conditions are right. Now consider that this exact sequence has already happened. It happened billions of years ago, in this galaxy, in this neighborhood of interstellar space. A massive star burned through its fuel, built an iron core, collapsed and exploded. Its debris enriched a molecular cloud. That cloud collapsed and formed our sun. The leftover material became our planets. The heavy elements from that ancient explosion became the rocks beneath your feet, the water in your oceans, and the atoms in your body. You are not merely observing the aftermath of a supernova. You are the aftermath. Every cell in your body is constructed from atoms that were once part of a star that died in one of the most violent events the universe can produce. The manganese activating the enzymes that build your cartilage and bones right now was forged during explosive silicon burning at temperatures exceeding 3 billion degrees. The copper, enabling the cellular respiration that keeps every one of your cells alive, was assembled through slow neutron capture during helium and carbon burning inside a star that still had centuries of fuel left, but was already manufacturing the instruments of its own destruction. The chlorine maintaining the acid balance in your stomach was created during oxygen and neon burning in a core that had already exhausted 3 previous fuels and was accelerating toward catastrophe. You exist because a star died, not metaphorically, physically, chemically, atomically. The supernova did not just create elements, it created the conditions for you. For all of this, for everything you have ever seen, touched, tasted, or loved, every sunset, every rainstorm, every mountain range, every living organism that has ever existed on this planet owes its material existence to the death of stars that burned and exploded long before Earth was a possibility. The real shock is not that stars explode. The real shock is that one of the universe's most terrifying acts of destruction is the same act that made worlds and oceans and life and minds capable of understanding what a supernova is. The universe destroys stars so that it can build everything else. And the fact that you are here, hearing these words, made of atoms forged in ancient stellar fires and delivered by explosions that shook entire galaxies, is the most extraordinary consequence of the most violent process in nature. Stars die in terror and fire, and from that terror and fire, everything you know was born.